I'd like to welcome everybody out there to today's presentation of Full Spectrum Science. Today we're going to be talking about exponentials and the environment, and this is our special Earth Day edition. Now, I am your host for tonight. My name is Ron Hipschman, and we're going to talk about growing exponentially in a finite environment and why that is just not possible. So let's just get right to it here, and we'll switch back to the slides. This was originally a talk that I have adapted that was given by Al Bartlett, a physics professor at the University of Colorado in Boulder. And Al thought that the greatest shortcoming of the human race is our inability to understand the exponential function. And that's exactly what we're going to do today. But don't worry about the math. Really, we're going to do some very simple arithmetic, and if you can multiply by 2, you're going to be okay. So what about this exponential function? What is exponential growth anyway? Well, exponential growth occurs whenever something grows by a fixed proportion. That's not a fixed amount, a fixed proportion in a given amount of time. And if you do that, it's growing exponentially. For instance, if you have an investment like a bank account, and let's say that it grows 5% per year, that's 5% growth rate. That's a proportion. It's growing by a fixed proportion each year, and hence it's growing exponentially. Let's take a look at that. Let's take a look at bank interest. For instance, let's look at the year, the amount you have in the bank, and how much interest you got that year. If we start off at the beginning with $100 in the bank and it grew at 5% per year, like we spoke about earlier, then at the end of 1 year, you would earn 5% of your principal amount in the bank. 5% of $100 is $5. You'd earn $5 of interest and end up with $105 at the end of 1 year. But at the end of the second year, you wouldn't get just $5 because you're going to earn 5% of the $105 in the bank. So you would get $5.25 of interest, and at the end of 2 years, you'd have $110.25. So you're getting more interest. And the next year, you get even more interest because you're getting that 5% of the principal amount. So in the next year, you get $5.51 interest, and in the next year, you'd get $5.79 interest. And in, say, the fifth year, you would get $6.08 interest for a total after 5 years of $127.63. So that's not doubling. I mean, that's just growing, but it's growing exponentially. It starts off slow, and then it's going to take off eventually. Now, one of the questions that people ask that's actually kind of interesting and something that you probably should know is, how long is it going to take my money to double? And you can figure that out very easily with a very simple equation. Let me show it to you. The doubling time, the time it takes to double whatever it is 70 divided by the percent growth rate. So in the case of our bank interest, if we are earning interest at 5% per year, we take 70 and we divide that by the 5%. 70 divided by 5% gives us a doubling time of 14 years. So after 14 years in the bank, we'd have $200. After another 14 years in the bank, we would have twice that. We'd have $400, and so on. This is growing exponentially. Let's take a look at what that might look like in numbers and in a graph. We're going to build an exponential curve. To do that, let's look at just doublings. Again, here we're just going to be multiplying by 2. So we're going to have the number of doublings and how many we have at the end of those numbers of doublings. So if we start out at 0 doublings, we have one thing, whatever that might be. It might be $1, it might be a grain of wheat, whatever it happens to be. After one doubling, we multiply that by 2, so we have 2. At the end of 2 doublings, we multiply by 2 again, and we have 4. At the end of 3 doublings, we have 8, and so on. Now, I think you could probably do this with me. After 4 doublings, we have 16, then 32, then 64, 128, 256, 512, and after 10 doublings, we have 1,024. Well, what happens if we put that on a chart? Now, the bottom axis there is the number of doublings, and the vertical axis is how many we have. So let's start off. At 0, we had a count of 1. We started off with one thing. After one doubling, we had 2. And then another doubling, 4. Another doubling, 8. and 16. And you can see here it seems to be growing very, very slowly. And that's one of the characteristics of exponentials. They start slowly, but they then gain momentum and they begin to increase much more rapidly. Let's continue. So we have 32, still slow growing. 64, oh, now we're getting a little bit off the x-axis there. 128, 256, now we're beginning to grow pretty rapidly. 512, and finally 1024. It really took off here. This is the shape of an exponential curve. It's often called a hockey stick kind of curve because it's kind of shaped like a hockey stick. Now let's do a little story about this. The story involves the game of chess, and it's going to involve a lot of doubling. It originated in India and in Persia. The story goes that a king asked his mathematician to invent a complex game that would be interesting to play. He came up with a game of chess, and the king was just amazed and delighted with this game of chess and told the mathematician that he would award him any reward he wanted. All he had to do was ask. And the mathematician says, I am but a simple man, and all I need is, my needs are simple. Let's take the chessboard, and on the first square, we are going to put 1 grain of wheat. On the second square, we're going to double that and put 2 grains. On the third square, we're going to double that again and put 4 grains of wheat, and so on until we get to the last square of the chessboard. Well, what happens here? Well, it's pretty easy to figure out how many squares are there on a chessboard. Well, let's number them. The chessboard is 8 squares wide. It's 8 squares tall. 8 by 8 gives you gives you 64 squares. 64 squares. And so we're going to have to do this 64 times. Now, don't worry, we're not going to have to do this all right at the moment. But let's look at that. So if we add 1 grain of wheat onto the first square, and then the mathematician said, just double it and put 2 on the second square. Double that again. Put 4 on the third square and 8 on the fourth square. And double that one more time here. And we're going to put 16 on the fifth square. And it's not really practical for me to do this graphically anymore, but we can run the numbers. So let's move our chessboard over and let's label the square number and how much wheat we add to each square. So on the first square, we added 1 grain of wheat. And I'm going to use a power of 2 notation for this because that's going to make it easy for us to figure things out. So 1 grain of wheat is 2 to the 0th power. That's equal to 1. As a matter of fact, any number raised to the 0th power is 1. On the second square, we have 2 grains. That's 2 to the 1st power. On the third square, we have 2 times 2, or 4 grains of wheat. On the fourth square, we have 2 times 2 times 2, because every time we multiply by 2, we put 8 grains of wheat on the fourth square, 16 grains on the fifth square, 32 grains on the sixth square, and 64 grains on the seventh square, and so on. Now, I want you to notice something. Remember that this power of 2 notation that you see over here, just the number in the exponent tells you how many 2's you multiply together to get this number over here. So 2 times 2 gives you 4. 2 times 2 times 2, 3 of them, gives you 8, and so on. Notice that this number here, the little tiny number in the exponent, is 1 less than the square number, always. 2 to the 4th goes on the 5th square. 2 to the 5th goes on the 6th square. 2 to the 6th goes on the 7th square. That gives us a clue how we can work this out for the squares that come near the end of the board. So, on the 62nd square, you put 2 to the 61 grains. That's 2 multiplied by itself 61 times. It's a big number. On the 63rd square, we add 2 to the 62 grains. On the 64th square, the last square, we put 2 to the 63rd grains of wheat. That's a big number. Now, if you want to, you can pause this video and multiply 2 times 2 times 2 with 63 of them and see what you get. You don't have to do that. I'm going to just tell you. 2 to the 63rd grains is this many grains. That's a lot. Want me to tell you what that is? That's 9 quintillion, 223 quadrillion, 372 trillion, 36,854,775,808 grains. That's a lot of wheat. But remember, that's just how many grains we put on the 64th square. It doesn't tell us how much wheat is on the chessboard totally, but there's a way to figure that out too. So I'm just going to put up a new chart here. I'm going to add to that chart, and we're going to see how this works out. On the first square, we have 1 grain of wheat, which is a total of 1. That makes sense. On the second square, we add 2 grains of wheat. That, plus the 1 grain we had before, adds up to 3. On the next square, we add 4 grains of wheat. That, added to the 3 grains we had before, is 7 total grains of wheat, and so on. 8 grains gives us a total of 15. Now let's look at this really carefully. Notice that the 15 grains of wheat is 1 less than the next, how much we're going to add on the next square, 16. The 31 grain total that we have here is 1 less than the 32 grains that we add on the next square. So notice that the number of grains we add on the next square is always greater than the total that we've added so far by 1. But this gives us a way to figure things out. This is 1 less than the next amount that we're going to add. So here on this square, on the 62nd square, we're going to have total 2 to the 62 minus 1, which is we're going to add 2 to the 62 to the next square. So the total will now be 2 to the 63 minus 1. And on the last square, we add 2 to the 63, which gives us a total on the chessboard of 2 to the 64th grains minus 1. That's twice the number of the 9 quintillion grains that we added. So it's about 18 quintillion grains. That is a lot of wheat. By the way, that would be a cube that's over 80 cubic miles of wheat, which would be approximately 5.5 Mount Everest of wheat. That's a lot of wheat. As a matter of fact, let me tell you how much it is. 2 to the 64th grains, or 18 quintillion grains, is 407 times the entire 2016 world harvest of wheat. That's a lot of wheat. Now, I happen to like M&Ms, so I wanted to calculate how many M&Ms that was. 2 to the 64th M&Ms would completely cover the entire surface of the Earth 362 times. You'd actually be shoulder deep in wheat. There's another thing we can do that is doubling. That's kind of fun, and we can do this as a little project ourselves. Go and get a piece of paper. And if you get a piece of paper, we can fold paper, and we can fold it, and every time we fold it, we're going to get double the number of layers of paper. Now, I measured this paper. It's 4/1000ths of an inch thick. So this is 4/1000ths of an inch. If I'm going to fold it in half, and you can do the same with your paper. Now I've doubled the number of layers by folding it. I now have 2 layers of paper, 1, 2, and I have 8/1000ths of an inch of paper. Let's keep doing that. How many times can I fold this piece of paper? Okay, I'm going to fold it over again here. There we go. I've now folded it twice. So I've doubled the number of layers. I now have 4 layers of paper in here. Let's double it again. I have now 8 layers of paper. I've folded it 3 times. I have 8 layers of paper. If I fold it one more time, I'm now going to have 4 times I've folded it. I now have 16 layers of paper. One more fold. I'm going to have 32 layers of paper. And I think I can get one more fold out of this. Yes, I can get one more fold. I have now 6 folds of paper, and I have about 64 layers of paper, which adds up, if you multiply that 4/1000ths original, I have about 1/4 of an inch of paper. I can't fold this anymore. I need tools or a hydraulic press or something to fold this. But let's take a look at the figures here. Let me switch back to the slides. Here we have our folding paper with 4/1000ths inch thick paper. We started off with 1 thickness, 0 folds, and that gave us 4/1000ths of an inch. We folded it. We had 2 layers, and then 4, and then 8, and then 16, 32, 64 layers added up to 1/4 of an inch. But let's say we have a very large sheet of paper. We could probably fold it more. If we had a very large piece of paper, we could fold it maybe 10 times. That would give us 1,024 layers, or about 4 inches thick. And I happen to know that the Mythbusters did this, and they started with a football field-sized piece of paper, and they were able to fold it 11 times, which meant they had 2,048 layers, about an 8-inch thick piece of paper, a pad of paper there. But if you keep going, for instance, 12 folds, you'd have more than a foot thick, and why stop there? Let's just go ridiculous here. If you could fold it 24 times, you would be a mile thick. It would be a mile thick piece of paper. You'd have 16 million layers in that. The next one, you'd have 2 miles, and then 4 miles. If you could do 37 folds, it would be 8,677 miles. It'd be thicker than the diameter of the Earth. And if you go all the way out to 42 folds, it would be from here to actually past the moon, slightly past the moon. So exponentials start slowly, but they build up quickly. Now, what else grows exponentially? Bacteria are a good example. Here we see the very beginnings of some bacterial growth. There's 4 bacteria here, and bacteria normally double about every hour. So if we let these bacteria double, instead of 4 bacteria in 1 hour, there'd be 8. Let's look at this as a time lapse, though. Then we would have 8, and then 16, and 32 is 64, 128, 256, 512, 1,024, 2,048, 4,096, 8,192, and so on. But eventually you realize there is a limit here. The bacteria do eventually run out of room, and they run out of food, and they run out of ways to get rid of their waste, and so on. So there is a limit to this growth, which is the resources. And that's one of the things we are going to talk about since this is an Earth Day presentation. We're going to talk about resource usage and environmental concerns. So let's look at the bacteria again real quickly, except this time we're going to invent a bacteria that double every minute instead of every hour. And I'm going to put 1 bacterium in this jar at the bottom of the jar, and I'm going to do that at 11 o'clock a.m. So you see the bacterium down there at the bottom of the jar? Since these double every minute, at 11:01, there'll be 2 bacteria. At 11:02, there will be 4 bacteria. At 11:03, I think you've probably guessed this by now, we have 8 bacteria, and so on. So I just want to kind of leave these bacteria alone. I'm going to leave the room, and I'm going to come back at noon and see what's going on. So I come back at noon, and I notice the jar is completely full of bacteria. Well, let me ask you a question. At what time was this jar half full of bacteria? I know it's kind of tempting to say, well, if they started at 11 and this is now noon, they were half full at maybe 11:30, but we know that's not the case because bacteria double every minute. So this jar was half full not at 11:30, but 1 minute before noon at 11:59. At what time was the jar a quarter full? I think you're going to get the hang of this. It was a quarter full a minute before that at 11:58. And what time was the jar an eighth full? Yep, you guessed it, 11:57. Only 3 minutes to noon, with the jar only 12.5% full, and the remaining space unoccupied. 87.5% of the space is still yearning for development. Look at all that space the bacteria can move into. Plenty of space. But we know it's 11:57 and the bacteria only have 3 minutes. Did the bacteria realize this? Did they realize they had a problem? Let's say they did. And at 11:57, the bacteria sent out expeditions outside the jar to look for new resources, new jars to move into. And they searched all over the world. They searched in the Gulf of Mexico. They searched on the north slope of Alaska. They searched in Saudi Arabia. And they searched in Iraq and Iran and Kuwait. And lo and behold, just in the nick of time, they found not 1, not 2, but 3 new jars. This is surely going to supply the bacteria with enough space for a long time to come. Well, let's take a look at the situation. At 12 o'clock, we know 1 jar was absolutely full. But remember, the bacteria double every minute. So at 12:01, now have 2 jars full of bacteria. At 12:02, 1 minute later, we double again and we filled all the jars. You cannot continue to grow exponentially like this. You will always outstrip your resources. So our population is growing exponentially as well. Check it out. Here is the Earth's population from 10,000 BC till about today. And you'll notice here, we start off and the exponential starts very, very slowly, the hockey stick, and eventually it just takes off. Until today, we have over 7 billion people on the face of the Earth. Now, a very interesting site to go to, and I highly recommend it, is this one right here, www.census.gov/popclock. And there you can look at the current population of the Earth, and you can see how it's growing. Now, how is that changing? Is that changing at all? Are we still growing at the same rate now that we always have grown at? Clearly, you can see that this curve is a little jagged. That population has changed its growth rate every once in a while. Well, let's look at our growth rate since 1960. Here, we're looking at the percentage growth rate over here on this axis right here. And remember, we can figure out the doubling time by taking this number, and 70 divided by this number gives us the growth rate. So through the 60s and 70s, we were pretty much growing at a 2% growth rate, which meant we doubled the population on the planet every 35 years. But we're making progress. The curve we're going down in our birth rate, and right now we're approaching 1% growth rate, which means we're doubling the population about every 70 years. But that's still not good enough, because that means there's going to be twice as many people on the Earth, over 14 billion in just 70 years. Within the lifespan of kids that are living right now, can the Earth support that? Well, we know it can't, because what time is it on our clock? Well, it's only a few minutes before noon, so we have to be careful about what we do in the future here. We need to drive this curve down faster than you see right here. We need to drive it down not to 0.4%. We need to drive it down to 0. And let's talk about those resources. What about our resources? Say, for instance, fossil fuel. Fossil fuel, we're increasing our usage of it by 7% per year. What does that mean? Well, we know how to figure out our doubling time for fossil fuel. It's 70 divided by 7%. It's 10 years. We double the amount of fossil fuel we use every 10 years, which means, remember the chessboard? In the next doubling time, we use more than in the entire previous history of doublings. That means in the next 10 years, we're going to use more fossil fuel than in the entire history of the Earth. Let's see what that looks like. Let's say this little square here represents the amount of energy that we used before 1960 in the entire history of the Earth up to 1960. That means that in the decade of the 1960s, we use that much energy. We used about the same amount. In the 1970s, we used this much. In the 80s, we used this much. In the 90s, we used this much, doubling every time, every decade. In the 2000s, we used this much. And in the decade that we just completed, the 2010s, we used this much energy. Well, we're into a new decade. It's 2020. And if we are to continue through the next decade, we are going to have to discover, extract, and refine this much fossil fuel. Can we do that? What time is it on the petroleum clock? How many minutes to noon? Well, what do the experts say? Well, here we have a report to Congress that says at the current rates of output and recovery, these reserves can be expected to last 500 years. Do you see the gotcha in that sentence? I'll highlight it. At the current rates of output and recovery, no growth. Here's another one from the World Coal Association. There are over 860 billion tons of proven coal reserves worldwide. This means that there's enough coal to last us around 118 years at the current rates of production. And I'll bet you caught that one, didn't you? At the current rates of production. No growth. So with growth, this will not last 118 years. Here's the Journal of Chemical Education. I don't know where they got their figures from. They say our supplies of petroleum and oil shale are extremely large, enough to last 7,000 years at present rates of crude oil consumption, no growth. Our proved coal reserves are enormous, at least 120 billion recoverable tons, and these could satisfy present U.S. energy needs for nearly 1,000 years. Of course, the U.S. isn't the only player in the game here, remember. Well, you can find figures and figure this stuff out yourself. There's a wonderful website, the U.S. Energy Information Administration, www.eia.gov, that has figures for the world reserves of petroleum and coal, and you can just figure this kind of stuff out. They say that the world reserve of petroleum is about 1.5 trillion barrels of oil. And we consume it, we know how much we consume a year, we consume it at the rate of 32 billion barrels a year. Well, we can do the long division. Let's just do the long division to find out how many years this is going to last. And if you do this long division, and this does not include any growth, petroleum is going to last 47 years, and that's at the current consumption rate. No growth. What about coal? There's about 948 billion tons of coal in the ground, and we're using it at about 8 billion tons per year. Well, do the long division. With no growth, that coal is going to last 117 years. No growth. Zero growth. What does the National Petroleum Council have to say about this? Restrictions on energy demand growth could prove to be expensive and undesirable. The Council flatly rejected any conservation-type measures, proposing instead the production of more energy sources domestically and the easing of environmental controls. This is ridiculous. This is like the patient suffering from cancer, and after careful study, the doctor prescribes the remedy. Give the patient more cancer. Well, let's look at what extraction of petroleum looks like now and in the future. Here's a curve on a graph, and this graph starts in 1900, and it goes to about 2020. And the blue curve here, you see, the kind of the turquoise curve, is a theoretical extraction rate that you can expect. Why? Well, this was actually come up with by a fellow named Marion King Hubert. It's called the Hubert curve. He was an American geologist and geophysicist. He actually worked for Shell Research in Houston. And even as an oil company scientist, he understood that as you extract, here we go, at this end of the curve, as you extract oil from the ground, it's easy to extract and you can grow exponentially at first. But the more oil that you take out of the ground, the harder and rarer it becomes. And so eventually you're going to get to a point where it's much harder to pull oil out of the ground, and you're eventually going to reach a peak. This peak oil he predicted happened in 1970. And then you start sliding down this side of the curve as oil gets rarer and harder to extract. Well, the pink curve here is the actual data of how much oil we've taken out of the ground. And you can see it follows the Hubert curve pretty closely. There was an oil glut, actually, in the early 70s. And then we started falling down the curve, just like he predicted, except we discovered a somewhat new resource. And that was a way to extract petroleum and fossil fuels from the ground, and that was fracking. And that's given us a little extra time. Not much. It might give us an extra 10, 20 years on this curve, but eventually this is going to get hard to extract as well, and it'll follow down the curve. So the Hubert curve kind of predicts the fact that we are in a kind of a time now where oil is somewhat easy to extract, but eventually it will run out and become expensive and difficult to get. And of course, there are environmental concerns. We're talking about Earth Day today. What are those environmental concerns? Well, here on the slopes of Mauna Loa, right up there is the NOAA Atmospheric Research Lab. Here's the lab itself. This is the Keeling Lab. Keeling was a scientist who first started measuring CO2 in the atmosphere back in 1958. And his measurements form what we now call the Keeling curve. Let me show you that. Here's the Keeling curve. The red line, that jagged red line, is the CO2 measurements starting in 1958 up till now. And you'll notice that it looks kind of like an exponential curve. It's now beginning to increase faster and faster. We started back in 1958, less than 320 parts per million of CO2. And as we move up through the years, we're now above 400 parts per million of CO2. Now it's becoming a little critical. Notice that it wiggles, by the way, that red curve wiggles. It wiggles because of seasonal differences. If we zoom in on that, you can see here that it goes up, and it comes up during the winter months and down during the summer months. During the winter months, plants die and release CO2 into the atmosphere. And in the summer months, spring and summer months, we have plants growing and taking CO2 out of the atmosphere. So that's why this line is kind of wiggling right here. It has a seasonal difference. Now, this is also measured at the South Pole. Here's the South Pole Station, which I had a chance to go and visit. This is their atmospheric research station, and this is also being measured down there. So we have good figures for both Northern Hemisphere and Southern Hemisphere. And we're now at about 414 parts per million of CO2 in the atmosphere. We went up by about 0.6% in the last year alone. And that is, of course, accelerating. So what can we do about this? Well, one thing is alternative energy. We can put solar panels on our roof, and this is the Exploratorium's roof. We have 5,874 solar panels. We're trying very hard to be net zero, so we're not pulling any power from the power company on the balance. We can also install wind. These are both renewable resources. But remember, we can install all the solar we want. We can install all the wind farms we want. That's really just still finding empty bottles like the bacteria we're trying to do. We not only need to find new resources and renewable resources of energy, we need to decrease demand. And the only way to do that is to stabilize or decrease the population. So in that vein, can we fix the population problem? Well, we can just look. What tends to increase the population? What tends to stabilize and reduce the population? Well, let's just list them out. Obviously, motherhood and fatherhood tend to increase the population, and small families and family planning can stabilize and reduce the population. The next one is actually really interesting, and that is increasing the population. Ignorance and disenfranchisement seems to increase population, whereas if we educate and empower, especially women, the fertility rate drops, and their families are smaller. So education and empowerment of women, extremely important. What are some of the other things that increase population? Well, peace tends to increase population, and war tends to decrease it. Public health, you live longer, you have great doctors, but on the other side, you have disease and plague and zombie apocalypses and things like that that decrease the population. Agriculture, we feed more people. We can increase the population. Famine, that tends to decrease the population. Law and order, that tends to increase population. Murder and anarchy decreases it. Clean air and clean water, well, that's good for us, but it's bad for population, whereas pollution tends to stabilize or reduce population. And safety regulations, well, those also are on the increased population side, whereas accidents tend to decrease or reduce the population. But let's look at this now. We have a list here. If we know that we cannot continue to grow exponentially in a finite environment and that we probably should stabilize or reduce our population on the Earth, here is a list of ways to do it. Now, we live in a very privileged time right now. We live in a time where we have the opportunity to choose from this list right here. Now, I'm hoping that we choose from the top of the list. If we do not choose from this list, it's almost guaranteed that nature is going to choose for us. And nature is not going to necessarily choose from the top part of this list. Nature will choose from the bottom part of the list as well. So right now, we live in a very special time. We have the opportunity to do something about our problems and our exponential growth. So let me give you a couple of parting questions by Al Bartlett. Al Bartlett says, can you think of any problem on any scale from microscopic to global whose long-term solution is in any demonstrable way aided, assisted, or advanced by having a larger population in our local, state, national, or global levels? Stated kind of the same way. Can you think of anything that can get better if we crowd more people into our cities, our towns, our state, our nation, or on this earth? One of Al Bartlett's favorite cartoons was this one. Thinking is very upsetting. It tells you things you'd rather not know. Thank you very much for listening to my talk about exponentials and the environment. We hope that you're going to enjoy your Earth Day, and we hope that you have a very good day indeed. Thank you very much.